So the theory which I now presented is a theory that when we do quantum mechanics, this is what we are doing. We're looking at a completely deterministic system where things just move according to some fixed rule, no probabilities anywhere inside in the fundamental laws of nature. Things just move, like planets in a planetary system do, or like all sorts of objects, and there's no quantum mechanics, but quantum mechanics is used as a tool. Quantum mechanics is used to write down everything in terms of matrices and to manipulate those matrices in fantastic ways as you're used to, and then we call that quantum mechanics. That's the theory. Now, many people who study the foundations of quantum mechanics arrive at the opposite conclusion, that this is fundamentally impossible, and that you have to have, we are not only married to quantum mechanics, we'll die together with quantum mechanics. I mean, there's no alternative according to most people who do foundation of quantum mechanics. I don't believe that. I think the Planck scale is very, very far away from us, so far away that from where we are now, the standard model, to the Planck scale, which is some 19 orders of magnitude, so many things can happen that even quantum mechanics can go down the drain, even though people don't understand today how that could happen. But, so the theory is that at the Planck scale everything is discrete and deterministic. If so, that could well be a new handle on making standard model-like theories. So this is why I think this will ultimately be important. I don't intend to be a philosopher. I want to be more than that. I'm a physicist. I want to see if there are new pathways to constructing models that are significant in understanding nature and not just for our philosophical field of well-being. It's more than that. So that's the theory, and the theory has been objected against very, very strongly by some people. So let me, what I'm going to do now is first I'm going to tell you why I like the theory so much and what the good things are. And then at the end we can discuss at length the problems that are still there. I showed you the problem of locality and my temporary resolution of the problem. It's temporary because it's not the whole story, second quantization. There are subtleties, in particular when you introduce interactions. The second quantization is fine for free particles, but when particles interact, things get more subtle, and when the interaction can be kept completely local is something that remains to be seen. But I'm not sure if I have time to discuss that any further. But the good things, I think, are the problems that people have with ordinary quantum mechanics when they refuse to see there could be such a simple deterministic system behind it. Then, if you don't see that, you have a fundamental problem with measurement, with collapse of the wave function, with, of course, Schrödinger's cat, and Born, who wrote down that if you take the square of the wave function, you get the probabilities. And all these aspects of quantum mechanics are mysterious in ordinary quantum mechanics. Whereas in this system that I'm describing, these aspects come out beautifully, I think. So this is the easy part. I'll tell you why these are things are so easy. The beables, I call them ontological. A way of saying that they refer to what is really going on. So when you talk about neutrinos, the theory is what's really going on are these sheets that move around. And of course you might think, well, it can't really be something more complicated than that because there's interaction between the sheets, so I have to think deeper than just that, okay, fine. But the ontological degrees of freedom could be as simple as sheets moving around. They're ontological. And the quantum states we are usually looking at are called templates. And templates is simply this: that I take a the B's could be the B rolls, but I take superpositions of the B rolls, and those are called templates. The theory I'm talking about is that what we normally do when we quantum mechanics, such as the hydrogen atom, or when we discuss neutrinos in the usual basis, then there are superpositions of the B roll states, and I call those templates. They're just useful for doing calculations, but they're not describing what really goes on. These things are describing what really goes on. But if you take a quantum superposition, you are just displaying your ignorance about what is really going on. That's a fundamental idea. But now, there is a third set of states, which are classical states. And classical states are people, are cats, or whatever, like or plants, like the planet Earth, going around in the sun. Those are classical things, and they are large, and they are the outcomes of an experiment. So I should also say, when you measure something like the needle of a detector points in a certain direction, that's classical. When you measure something, the outcome is classical. The gigabytes of data that come out of the LHC are classical data. So all these things are classical states, and now I want to describe to you the relation to the two. And, well, the argument I want to present is the following, and it's a very important argument, that the classical states are also variables. And the reason for that is rather strange, because this claim is saying the following thing. We have, say, Planck scale, let's call it Planck. Although we're not sure where exactly Planck length sits. Maybe 10 to the minus 35 meters, maybe some other distance scale, but in any case, very, very scale. Then there's ordinary micro states, which are called quantum mechanical, and then there are classical states. And Planck states, there are very, very many of them. These are the templates. And actually, when we describe the hydrogen atom or other states, we are describing states very, very close to the vacuum, and then there are much fewer of them. So the templates, there are just a few of them, not hardly as many as these. And classical are still fewer of them, because many, many different hydrogen atoms you can use to describe the same detector at the same position. So those are very much fewer. Now the templates all are superpositions of the superposition of the microstates. And these lines tell you that they're all superpositions. The classical states are also superpositions of all the templates. So all these are superpositions, like that. However, if I look at these microstates and these classical states, there's a one-to-one mapping. Or rather, every classical state corresponds to a whole set of Planck states, but they never superimpose. So,